Hello and welcome to the live webinar about planning a discharge measurement system with Stefan Sietschlag. My name is Helena Wingert and I take care of the organization today. Before we start, I would like to tell you something about today's referent or presenter. Stefan Sietschlag is a graduate engineer with a specialization in civil engineering and water management and has been working for Hydromet since 2002. Here he started as business development manager and is now product manager for hydrology with specialization in discharge measurement. Since 1986, when he started his professional life, discharge measurement technology has been his area of expertise. Since 1998, he has been holding seminars and trainings on this topic, and besides, he is chairman of the Working Committee Hydrometry at the Dean Standards Committee Water Management. Before we start, I would like to tell you how you can ask questions and when we will answer them. The webinar will last about 45 minutes and end with a question and answer session. If you have any questions, you can always type them into the provided text field, which you can find in the GoToWebinar menu. We will answer them collectively after the presentation. If there occur technical problems, I can answer them directly in typing. After the webinar, a short survey will pop up and we would appreciate it if you fill it out for us. That's it from my side. I now hand over to Stefan.
Thank you, Helena, for this nice introduction and welcome to the webinar today with the topic hydraulics in rivers and open channels for site selection for continuous flow meters. I want to invite you for a short walk across the hydraulic world and with the targeting that we have a little bit more knowledge what we should keep in mind if we go out in the field and look for a good site where we can deploy a side-looking Doppler or either a surface velocity radar, because these both instruments are the continuous flow meter sensors we have in our product portfolio. You see here a short agenda for this day. So firstly, we will clear up some definitions around hydraulic and discharge. I will talk a little bit about hydraulics in open channels, and you don't need to be afraid. Usually hydraulic is linked to an enormous number of formulas and equations and lots of mathematics. So I will keep it as simple as possible so that you see maybe 1, 2, 3, or 4 more equations, but you don't need to compute anything. You should just get an impression on what you should be careful in the field and with respect to hydraulic conditions on site if you make a site evaluation. We will talk about what the velocity index method is, because this is the method which is finally used for computing discharge with your flow meter. And then I will show you shortly with one slide the device continuous measurement system, how it works. So what is the principle of SBR 100 and what's the principle of a side-looking Doppler? And finally, the biggest part in this webinar is recommendations for site evaluation. Okay, let's start with the first question. What is discharge? Discharge, and there's a definition which you can find in an ISO standard 772. Hydrometry, a vocabulary and symbols. Discharge is defined as the volume of liquid flowing through a cross-section per unit of time. And Q, this is the symbol for discharge. Vm is the mean channel velocity or the average velocity in your cross-section. And A, this is the cross-sectional area, which you can compute from knowing the bathymetry and measuring the water level. What is hydraulic? Hydraulic is a topic in applied science and engineering dealing with the mechanical properties of liquids. Free surface hydraulics is the branch of hydraulics dealing with free surface flow, such as occurring in rivers, in canals, in lakes, in estuaries, and seas. Its subfield open channel flow studies the flow in open channel. Very clear and simple expression. You can find this on Wikipedia. The scientists who dealt with hydraulics in the past, here are some of the famous ones, which is, for example, Thales von Millet, Aristoteles, Archimedes, the buoyancy in liquids, Hero von Alexandria, Evangelista Torricelli, who has defined the law for outflow out of a bucket, for example. Giovanni Pollini, formula for weir structures. Daniel Bernoulli, some of you will know the Bernoulli equation for steady flow in open channels. Or Robert Manning equation for flow in open channels, also a very famous one. There's one guy which is not mentioned here, but also has done some very important investigations, Leonardo da Vinci. He described the resistance of riverbed and sides to the free surface flow and its effects on the velocity distribution as follows: the water of straight rivers in the swiftest is farther away it's from the walls. Because of resistance, water has a higher speed in the surface than on the bottom. And this happens because water on the surface borders on air, so there's a little resistance. Water on the bottom is in touch with the ground. We have a higher resistance. This finally causes the more or less logarithmic velocity distribution if we have a free flowing waterway. We'll come to this point later again. Why do we need knowledge of hydraulics in open channels? I mean, this question is for everyone. Those of you who are doing daily measurements in the field with mobile portable flow meters, you have to select the right position, the correct position for your vertical, for your measurement vertical. You have to select the right method for the velocity measurement, which can be a multi-point method or one of the reduced from the ISO standard 748, just like 3-point, 2-point, or a 1-point measurement, or the surface measurement. So, and the question behind is, why is the 1-point measurement representative for the average velocity in this section, in this vertical? And this is something which is linked to hydraulic knowledge in open channels. We need hydraulic knowledge to optimize the site selection for discharge measurements. We need it to optimize the discharge measuring procedures. We need it also for good installation and deployment of continuous sampling instruments like ODD/SLD or side-looking Doppler or surface velocity radars. We need it to do hydrometric calibrations of online monitoring systems. And of course, we need it also to develop and maintain velocity index ratings and develop and maintain the rating curves. Now we come to the classification of flow. We have two different types of movement. The first one is falling movement. And falling movement means the water is going from a higher elevation to a lower elevation without touching any boundary around. This could be a weir structure, the flow over weir structure like we see here. Or this could be also the flow out of, if you have a yield of a spring somewhere on the mountains and you want to collect the water, you take a bucket of maybe 20-liter volume, you measure the time until it is full, and you know exactly you have maybe 20 liter per second outflow, the direct measuring method with falling water. And we have, of course, on the other hand, the flowing movement where the water is flowing in the riverbed, is touching the river banks and the bottom. So you have a resistance on both sides, the bank and the bottom. The flowing movement, furthermore, is distinguishing between steady flow and unsteady flow. The steady flow, if the velocity at a given point doesn't change with respect to the time, then the flow is called steady. If you look to this hydrograph here, you see the discharge over the time, and it does not vary. It's more or less always on the same level. It's around here, in this case, 9 cubic meter per second, and doesn't change over time. Unsteady flow means if the velocity at the given location changes with respect to the time, then the flow is called unsteady. You see a hydrograph for unsteady here. For example, the water discharge goes up and down over the day. And this could be, for example, if we have somewhere upstream a water treatment plant, which is distributing the water over the day with different amounts because it depends on how many water is used in the households or in the industry, which is connected to the water treatment. Other examples for steady flow. This is, for example, steady if the weir structure is fixed. You do not move the weir and you have always the same water level upstream. Then you have steady flow, always the same amount of water going down. Unsteady flow is, for example, a flood situation. You see here our gauging station in Kempten, where are the main facility. And this is the River Iller in the back. You see this was during a flood situation some years ago, where a huge amount of water is coming downstream, and this water varies over time. So that means we have unsteady conditions. Furthermore, we classify the flow in laminar flow and turbulent flow conditions. And to understand this, I have made a small drawing here in the middle. You see a bucket where we have inside a tube with a colored fluid. The water level in the bucket is non-varying, but there's an outlet tube here where you see also the red color is going in. If we have a low flow in this tube, then you see the red line of this colored fluid, which does not move. Turbulent flow, you have a mix-up. That means in low flow conditions, the particles move along a way. So streamlines are not mixing. In turbulent flow, they do. In turbulent flow, the particles move in irregular paths which are not fixed with respect to time and space. The flow is then mixing up. Laminar flow, an example from the laboratory in the university, is the laminar table. You are looking from on the top down to this table. There's a glass plate, and below there's a small, maybe 5 millimeter space where water is moving, and you see also the green lines coming from colored fluid. You see they don't mix because the water is so slow moving below this plate. You see the obstacle here where the flow lines going around, but you don't have turbulent condition because never don't see any mixing of the colors. And if you look from top, the velocity distribution looks like this if you have laminar flow in a channel. Turbulent flow is the normal flow in the river, and then the velocity distribution looks like this. In nature, and this is the very important, there is predominantly turbulent flow condition. And this is very good for us because turbulent flow conditions, we have a redistribution of everything in the water. So we have turbulent packages going up from the bottom down to the water surface. The water is well mixed, and then you have also a good velocity distribution, which is predictable. So it makes flow uniform in long term, and it makes velocity profiles predictable. You can compute them with logarithmic functionalities and so on. You have a predictable velocity distribution also across the channel from the left to the right bank, and you have a large short-term flow variability, which means if you go to a single point in your water cross-section and you are measuring the velocity, then you have a lot of variations. This is also the reason why we, for example, in potable flow meter applications, we are measuring with a certain time, for example, for magnetic inductive probes or for mechanical type meters, the minimum measurement time is 30 seconds to get a good average due to this short-term flow variability. If you look to the velocity distribution in turbulent flow conditions, you see it depends on the roughness on the bottom, how the velocity distribution looks like. If it is a very rough bottom with big obstacles and stones, the velocity is lower on the bottom. And then you have this slope like the red line. If you have a smooth bottom, like made a channel of concrete on the bottom, then the velocity distributions look more like the green line here. It's more like a square. If you look to the average velocity, which means the area of this square is the same as the area below the logarithmic distribution, the average velocity, then you see that you will meet around 60% below the water surface. That means at the 6/10 depth, you will meet the average velocity with your red curve here. And this is the reason why a one-point measurement, where the measurement point is located at the 6/10 depth below the water surface, is for free-flowing water courses representative for the mean velocity in the entire measurement vertical. Furthermore, we distinguish in the classification of flow between subcritical, critical, and supercritical flow. What does that mean? We make an example to recognize whether the river is moving subcritical or supercritical, you can go to the field, you take a big stone, you go on a bridge, and then you throw the stone from the bridge down into the water and observe the waves which are spreading out. And you will see the point where the stone is dipping in the water. You have waves moving all the way around this point, and the point itself is moving with the velocity of the flow of the river downstream. And you look to the waves and you see what happens. If there's only a movement around the dip in point, the water is not moving, the velocity is 0. If the velocity of your river is lower than the velocity, if the velocity is lower than the W is the velocity of the wave, then you have waves which are going upstream and also downstream, but the point itself is moving slower than the wave are spreading out. And if both is from the same size, the velocity of the water and the velocity of the wave, then you see something like this. We call this also standing waves or border conditions. This is the change from subcritical to supercritical flow. This is the critical situation. And in supercritical conditions, your velocity is much higher than the wave velocity itself. So that means the point where the stone has dipped in is so fast, faster than the wave can spread out. You don't have any effects for the downstream situation. You can also compute, or this is another illustration of this phenomenon. That means in the end, you have, for example, 1 cubic meter per second, and this cubic meter per second can flow with a high water depth in subcritical flow conditions, or with a very low water depth in supercritical flow conditions. And somewhere in between, there's the change, there's the critical flow. And you just need to change the slope of your bottom to accelerate the speed and to minimize the water level. So which means somewhere in between there's a critical point where you're changing from subcritical flow to supercritical. And in order to compute, and here we have the second formula of this webinar, is my flow subcritical or supercritical? You just need to take the Froude number. The Froude number is the average velocity divided by this root cause of square root of the gravitational acceleration times the mean water depth in your section. And if this number is less than 1, your flow is subcritical. If it is equal 1, it is critical. And if it is bigger than 1, you have supercritical conditions. Please keep in mind, for discharge measurement sites, it is always recommended to have subcritical flow conditions on site. Froude number should be less or equal 0.5. Velocity distribution across the channel, also a very important point. If you look to a circular channel, you see the velocity distribution is more or less symmetric. So you have the maximum on the water surface, and then each black line is represented for the same velocity. We call this isolines here. And you see the velocity distribution for such a circular channel. If we look to a rectangular channel, it could be look different. The maximum velocity is not on a water surface in this case, it's inside the cross section. And this is caused by secondary flow, which is moving from this point. So flow components which are affecting the maximum velocity in the middle, and forces which are bringing the max below the water surface. We call this in hydraulics the so-called dip-in effect. And this effect is as more detectable as smaller the rectangular channel and as deeper it is. So a small channel with a very big water depth will create the dip-in effect, which means the velocity distribution looks then something like this in the middle. And this is not logarithmic, and this is also not easy to predict. That means if you have, for example, a calibration model, or you take a software to calibrate your site with these conditions, the normal calibration approach with logarithmic distributions will not work. You need to do site evaluations and site comparing measurements to set up then an index for the site. If you look to trapezoidal shaped channels, also here it's possible if it is a very narrow channel and very deep that the maximum velocity will dip in, so will drop below the water surface. If you have natural rivers, it can be that you have two maximum velocity areas depending on the shape of the cross section on the bathymetry. And what is always very important, that the distribution of your velocity across the channel should be homogeneous and predictable. Because finally, with your flow meter, you're measuring somewhere in the cross section, and you need to build up a relationship between your local measured velocities and the average velocity in the channel. How do the instruments work? Just a brief explanation about these two different sensors. The surface velocity radar is a radar sensor and works with electromagnetic waves. You see the radar is pointed to the water surface by an angle of maybe 30 degrees. It's transmitting electromagnetic waves and it is receiving reflections from the moving water surface. A very huge assumption you need to make is you need to have a rough water surface, otherwise velocity radars will not work. And what you get back is the reflections with a Doppler shift, and from this you can compute the surface velocity. For side-looking Doppler, it's different. You have two acoustic transducers looking sideways into the water and transmitting sound in direction of flow and against the direction of flow, receiving the reflections from moving particles in the water. And from this you can compute also reflections come back with a Doppler shift. You will get the velocity along the acoustic beam, and if you know the geometry of your sensor head, you will have an X component which is in flow direction and the Y component which is pointed to the wall. So Y is usually 0 and the X component is used for discharge computation. You can set up cells. So with the SLD, you have always 9 cells. From our experience in the field, it makes sense to have bigger cells and just to work with 4 cell velocities. This is the sample volume, finally, which you can then use for doing the velocity index discharge computation. And what does it mean? Velocity index method. With the velocity index method, the mean velocity for the cross-section is determined from locally measured velocities. In case we have a surface radar, we have a footprint on a water surface. So we are measuring here in this add area. In case we have a side-looking Doppler, we are measuring in a sample volume, which is depending on the cell size, of course, and the blanking and the range of the frequency you have with your side looker. Finally, and remember the first equation we saw on the first slide, Q is V index, measured velocity, times correction factor times cross-sectional area. The product of the index velocity and the correction factor, this is the average velocity in our cross-section. What we need to define is finally the K value. For this, we provide a Protus2 software, which you can use to do the site calibrations. You can also do it by your own, and you can do calibration measurements in the field. You can compare the real existing average velocity from your calibration measurement with the measured velocity from your sensor. If you do this 5, 7, 10 times at different flow situations, you set up a velocity index rating. Now we approach recommendations for site evaluation, and what you should keep in mind if you plan to set up a continuous operating flow meter is, first, it's always recommended to go to our website and or to get in touch with our sales engineers and ask for our questionnaire. The questionnaire is a 6-pager which you can use to fill in some information which are very important for us to make a first size assessment. So you will be asked for the name, you will be asked for some for example, for the low water level, which can occur on site, for the highest water level, for the range of velocity. Is there wind effect? Is there any other effect? Is there, for example, traffic of vessels on the river? These are all very interesting information, which then gives us a little bit support in doing a diagnostic from far away. And also, of course, it's important to have the cross-section available, that we can have an impression what is how does the cross-section look like? Is it possible to deploy a side looker, or is there any obstacle in the cross-section that will reduce the range, for example? That's a topic we also will talk about in the afternoon, how to detect obstacles in the cross-section. And secondly, if possible, please take pictures from upstream and downstream situations on site. Please, if possible, take a tape and measure some relevant cable lengths, for example. You should have a deeper look to the bank characteristics, very important, in particular for side-looking Doppler, because you need to fix the instrument on site, robust, resistant versus flood situations. It should not be destroyed if there is a big tree coming downstream in a flood. So you need to make a very robust installation on site. You need to look at the hydraulic conditions. So what does here happen? Do you have any backflow? Do you have dead water zones? Do you have swirls, which are not recommended? And of course, you should also have a look to the logistic aspects. So do you have access to the site? Can you go with a big car with all this material you need for installing without having any difficulties on the way to the bank and to the finally dedicated site for installation? So this is something which you can do first. Secondly, there is, particularly for the side-looking Doppler, a guideline available, which is the ISO 15769, hydrometry guidelines for application of acoustic velocity meters using Doppler and echo correlation methods. And looking into this, there are some points which need to be considered during the site assessment. The first one, which is very important, you need, and this is also valid for the surface velocity radar, you need a straight course of the stream and a uniform cross-section and slope. You need a straight length upstream, should be at least twice that downstream. You will need to have a site where flow directions for all points on any vertical parallel to each other and at the right angle to the cross-section are. You need to make sure there's a regular velocity distribution in the vertical and horizontal plane of the measurement. You need to make sure the riverbed is stable and also the bank is stable at all stages, because the cross-section itself is part of discharge computation. If you have erosion on site or deposition and the bottom elevation will change, then the computation of the discharge in the end is affected by these changing conditions, and the index rating will be unstable. And what you should avoid is sites with backflow, sites with excessive air entrainment for acoustics here, dead zones where water is not moving. You need to avoid obstacles within the acoustic beams. You need to avoid aquatic growth in the cross-section. Highly turbulent sections should be avoided. And this also applies to sites with stratified flow, which is also not usable because of the unpredictable velocity distribution. The site evaluation starts always in the office. What you can do first is take maps, take pictures, taken from airplane, take Google Maps, whatever. You can check the course of the water, and the course should be as straight as possible, providing flow which is parallel to the banks without having irregular velocity distributions. The rule of thumb you can assume is that the water is flowing parallel to the banks if the water course is straight over a distance of 5 to 10 times the channel width. Look to the drawing here on the left. And according to the ISO I mentioned in the previous slide, it's recommended to have that the straight distance has at least the double length in the upstream direction as it has downstream from the measurement cross-section. This is the minimum requirement for continuous operating sites. You can check, and you should check, the direction of flow for flood situations. The direction of flow over the foreshore should be identical with the main flow. That means it does not make sense if the flow in a flood situation goes somewhere around the cross section. Sorry, this is a German picture here. You see here, AA is the cross section, and this is the way where the river takes. This is the straight length of the river, and this dashed line is the main flow way the river takes. And the same direction should be also in flood situations where the foreshore is overflooded with water. You should have always the same direction of flow, as you see here in the pictures, a station where we have mean flow situations and flood situations. Particularly for surface velocity radar, you can also in the office check your records you have for sites where you have already done portable velocity meter measurements. If available, take a look at existing discharge measurement records, and then take Excel or whatever and bring the surface velocity max, VO max in this column here, in relation to the average velocity on your cross-section, Vm. And if you see there's a good regression with a coefficient close to 1, this is a pretty good site where you can simply deploy a surface velocity radar, assuming you have enough roughness on the water surface, of course. Site evaluation continues then in the field. As always stated, you need to make sure you have parallel flow to the bank. And if you don't know, is it really parallel flow, you can take an experiment in the field, take something which is flowing on a water surface and observe the flow line. You can take a lemon, you can take an orange, you can take a plastic bottle. Okay, plastic bottle is not good because this is wasting the environment, but you can easily observe how it is moving. If it is moving to and fro or straight across the river, then you have cross flow. But if it's moving parallel to the bank, you see this is really parallel flow to the bank. You can continue with applying portable flow meters, for example, ADCPs, mechanical type meters, magnetic inductive flow meters, and you can check the results afterwards. Well-suited measuring sites have a regular velocity distribution and a regular measuring cross-section without any obstacles. See here, the maximum is on the water surface. Even here, that's the velocity magnitude plot from an ADCP measurement. You see the maximum on the water surface and then the velocity distribution across the channel. Site evaluation continues in the field. Keep an eye out for the confluence of tributaries. If you have from the site an inflow from the site, which is not always active depending on the situation, on the flow situation, or on rain events, on flood situations, whatever, these can create cross flow and affect the horizontal velocity distribution, which you can see here in this drawing. So the maximum velocity is shifted to the side where the inflow is coming. It's not suited for having a good velocity index on site. Stay away from flow control structures, and in particular from structures like here, where you have 1, 2, 3, 4 different gates, which then will be regulated independently and not in the same way. That means if, for example, 1, 2, and 3 are closed and only gate number 4 is open, you see the velocity distribution will look like this. The maximum will shift to the left side of the river. And if you have set up a surface velocity radar somewhere downstream, then you are not measuring in the area of the maximum flow. If you have a side-looking Doppler, also here the index ratio will be unstable because depending on how they regulate the wares, the velocity distribution will change across the river. And that's why stay away, and ideally the measuring site should be 5 to 10 times the width of the channel away from the structure. Avoid meandering river courses with shallow water depths. So this is a very shallow water here. You see the ground in this case. You see the water is coming from here and goes always to and fro in different, so you have cross flow because the river bed geometry is not uniform. So no parallel flow to the bank. Velocity distribution is not estimable. Sorry, it's a mistake here, not predictable, and we have unstable velocity index ratios. You should avoid measuring cross-sections with vegetation inside, as you can see here in this picture. Plants prevent mixing. Plants cause unpredictable velocity profile. Plants in the water, growing weed in the water is causing unpredictable flow distribution across the channel. And of course, in the end, unstable velocity index relationships. In addition, vegetation blocks the sound propagation of acoustic side-looking Dopplers, and vegetation can also cause measurement noise on the water surface when you are deploying a surface velocity radar. Avoid sites with backflow in parts of the cross-section. This is an example for this, what I mean. This is a river where you see here, it's very straight in this area. The curve is very far away. But on the right side of the river, there's some water coming back. And if you look to this, you see it's flowing in a circle here around the ducks which are swimming on the water surface. And setting up an index ratio here will not make sense because some of the water is moving in the other direction. It is caused by the geometry, of course. Maybe there was some deposition on the ground. But if you have set up an index ratio on this side, then you will need to care also for maintenance of the cross-sectional profile. So sites with backflow will cause unpredictable flow distribution and unstable index relationships. Site evaluation continues in the field. You should avoid sites with stratified flow. And how do you know it's stratified flow? You need to do measurements with, for example, ADCPs or other instruments, and then look to the velocity distributions. If you look to this velocity magnitude plot here from an ADCP measurement, you see there's a maximum on the in the upper layer, and there's another maximum in the lower layer. And in between, we have a zero line. If you look to the single velocity distribution, you have two more or less maximum areas here. The one point is here, the other one is here. This makes no sense. You cannot predict this velocity distribution. You have unpredictable distribution across the channel, and there's no index ratio possible. For surface velocity radars, particularly should avoid measuring sites where you have standing waves. What do I mean? If you look to this movie here, you have points where, of course, caused by the button structure, you have standing waves. If you are pointing with your radar on standing waves, this is not representing the flow velocity of the river. And also even here you have noisy data and not representative data. You should avoid measuring surface velocity in an area where you have macro turbulences. For example, the area here is not good for surface velocity radars, while the area below is pretty good. You should avoid the surface velocity measurement behind pillars. So if you go on this side, downstream, you see there's the pillar in the middle, and then you have a maximum on this side, and a little one is on the other side. If you have bridges where you have pillars inside, please try always to point with your velocity radar upstream to avoid any bad effects from the pillars itself. So finally, I have prepared 2 slides for you, which are summarizing the top 3 criteria for good radar sites and for good Doppler sites, acoustic Doppler sites. First one, to the surface velocity radar. Point 1, you should have a straight channel or river which with parallel streamlines, free of growing weeds and free of macro turbulences. This could be look like this, or this one here, which is an artificial channel in Italy. You should have uniform shaped cross sections with a stable riverbed and banks, regular velocity distribution, and a stable position of the maximum surface velocity, because this is where you are measuring with your surface velocity radar. You are pointing on a water surface. You have the footprint and the reflections, the energy which is coming back from this footprint is used to compute the velocity in the radar. And you will need a rough water surface. This is very important because if you don't have a rough surface structure and velocities, the greater than 0.1 meter per second, you will not be successful with radars. Rough water surface is important. A minimum velocity of 0.1 meter per second and a minimum influence of wind gradients. If wind is coming from the side, you can understand that the wind is shifting the waves not in direction of flow, but in direction from the left to the right or bank or reverse. And this also makes an exact and correct measurement of the velocity on a water surface very difficult. Top 3 criteria for good SLD sites. Same as before, straight channel, river with parallel streamlines, free of growing weeds and channel obstructions. That means any obstacle on the water bottom, if the side-looking Doppler is very close to the bottom, can be an issue. You need to have sections free of growing weeds, free of rocks and air entry through macro turbulences. Second point, uniform shaped cross sections with stable riverbed and bank and regular velocity distribution. And the third point is you need to maintain the distance from the measuring plane where you want to install your side looker to the water surface, respectively to the riverbed. This is the so-called aspect ratio. Aspect ratio is distance between sensor and end of the measurement volume divided by the distance to the next delimitation, riverbed or water surface, what even is in the closest distance. And a conservative value is aspect ratio of 10. So please keep in mind the aspect ratio is also depending on the transducer quality, on the frequency itself, so on the beam width of your acoustic transducers. We have good experiences, for example, with a site where we have 10 meter in width and just 15 centimeter water depth. And there's a 2 megahertz side-looking Doppler running, which is mounted 25 centimeter above the bottom. And we can measure really the full range. So this is really depending on the instrument and also on the site conditions. The conservative value is 10. But in practice, you can have even 20 or more. But this requires a site test in advance. Okay, so far so good for this brief introduction today and our brief walk across hydraulics of open channels. I hope it was somewhat interesting for you, and I'm now open for questions you may have concerning this topic. Thank you very much for your attention.
Thank you. There's one question about artificial water channels. So I have a question about the SVR. If I use the SVR 100 for discharge measuring of an artificial water channel for hydropower production, where water flow may stop, what does the SVR 100 measure in the situation of no flow? I will expect a 0 meter per second value or an impossible value.
Usually the range of the surface velocity meter is 0.08 meter per second up to 15 meter per second. So if the water is, if your power plant doesn't outlet, or the outlet is stopped or blocked and there's no flow on site, then obviously also the water surface will be smoother. That means we don't get enough reflections back. And for those situations, we have a signal quality index, which then is, of course, the velocity is then 0, or you get, zero velocity. You cannot measure 0, but you get the velocity either 0 or close to 0. And if it's going in reverse, you can also get a velocity with a negative sign. So that's not the point. But you need to look to the signal to noise ratio and to the signal quality index. And those indicators will give you an information about the situation on site finally. That's why we have this metadata with the signal quality index.
Okay. Do you have any further questions? We can say that SLD with a few centimeters of water over the sensor may be enough for the measurement.
No, and if you have time, I want to invite you to the data analysis webinar, which is in the afternoon. I have an example what happens if you are too close to the water surface. You will see this in the range check. So that means we have then side lobe effects. That means each acoustic transducer has a main lobe with a certain beam width and side lobes which are coming around the transducer. And side lobes are hitting very, very quick the water surface and then are reflected into the main lobe. And this causes interferences. So that means the values that you then receive, if you are too close to the water surface, they are affected by interferences and they are not accurate anymore. They are very noisy and you can't use them.
Actual conditions are often deviating from the theoretical optimal conditions. Do you have recommendations in case of small rivers with aquatic vegetation?
Yeah, the only one recommendation I have is maintain it and take, you need to cut this growing weeds periodically if possible, or you need to bring someone out in the field and do field maintenance, because this is a natural and environmental limitation. So if there is a section with growing weeds, your acoustic sound energy will be absorbed by the plants and the reflections coming back from moving plants in the water are totally different than from moving particles which are flowing in direction from upstream to downstream. So there's really no other chance than to either take maintenance work on site, do maintenance work on site and cut them, or consider to make civil works in advance and bring the cross section in a shape where plants cannot grow. There are different solutions available. Bring something into the bottom, some foil or grounding material where plants are not able to pass it or something like this. So we have a few sites here in Germany with geotex. It's called geotex material on the ground, and then the measuring field is free of aquatic growth. Of course, upstream and downstream you still will have the plants, but not in your acoustic beams. But this is really you need to spend much more money if you have a site like this, and you need to measure there. You need to make sure plants are not an obstacle.
Okay. Another question about the SVR100. I have a water channel with a velocity greater than 0.1 meters per second, but with flat water surface. If I force the roughness by placing chains on the water surface and I create roughness, are those waves still representatives for a good measurement?
It can work. We have, I know this from Italy. We have a guy in Italy that's doing this, and it works pretty good. So if these are not standing waves, so the waves are moving down with the water itself. So, and you have then, if you take chains, not that much, not hundreds of chains, but if you have chains which are causing a roughness, this can help, of course. It also depends on the width of the river and on the site conditions, but for smaller rivers, we have good experience with the chain solution at one site in Italy, as I know.
Okay, one question about the maintenance. Over what distance is it recommended?
Yeah, it depends on what you want to deploy. Is it a side-looking Doppler, the side lookers itself? So you know, to keep in mind the angle between the center line of your transducer head and the orientation of the beams is 25 degrees. So you can take a drawing of your site, a view from top, or I don't know, and then draw the side looker in, take the angles and look what is the range you want to achieve, and then you need to have, yeah, in direction of flow, at least the field where you are measuring with your beams, this needs to be free. So the length, something which you can easily draw or compute.
Next question. To what extent are the SVR100 and SLD applicable in closed channels? What are the major differences in the site evaluation approach?
A closed channel means sewage or something like this. Please keep in mind, both instruments are designed for open channel flow. If you have closed channels, and particularly if they are full with water, okay, it will not work. Maybe you can measure with the side-looking Doppler in the closed channel, but we don't have a calibration for this. So that means you need, so our Protus software is also only for calibrating and with free open surface flow. For closed conduits, also the surface velocity radar is maybe not the first selection. So we have other radars which can do this, for example, HAC floater. For side-looking Doppler in closed channels is possible, but you need to consider how you calibrate this finally. So this is not possible without Protus 2. You need to ask an engineering office or take own investigations or get in touch with the university or whatever to get a calibration for your specific shaped closed channel. And what else is important? Both sensors do not have ATEX. That means they are not for hazardous environments. So if you go to wastewater channels, this is not possible with SLD and also not with SVR100.
Okay, next question. May the SLD parametrization be changed remotely through odd data loggers?
Yes, I'm a little bit careful. I know the service team is doing this. If you take an NetDL and set it on transparent mode, then you can have access to the SLT itself. But if the connection is unstable and you lost connection, then the instrument maybe get lost in the field also. It's a little bit tricky. In this case, I recommend you please refer to our hydro service team. They can easily support you and can assist you in this case.
Okay, we are using SVR100. It is giving signal quality bad status, B. What is the standard process to follow the error correction?
For the SVR100, we have the signal quality index. We also we are still in the procedure to collect experience with this. So we have seen this, the signal quality could be good or could be bad, maybe 1, 2, or maybe 3. And the velocity itself looks not bad. So we will have, and this is something we found out during our site evaluations from testimonial sites, we will bring the signal quality index with the next firmware update in relationship with the signal to noise ratio, which is much more better identification of a good signal or a bad signal. At the moment, you will see outliers, and you need to make, of course, you need to check what has this outlier been caused by. Was it to rain? Rain could have an effect, so very strong rain. This is something we will talk also in the afternoon about how we can analyze the data for surface velocity radar.
So here's one question from somebody who is quite new to that topic. What is the right sensor for flow discharge monitoring in small drain discharge at factory final discharge point?
It depends on your your channel. If it is an artificial channel, maybe it's a rectangular or it's an egg-shaped or whatever. So it's a small channel with, I don't know, only 1 meter in width and just 1 meter in depth, something like this. You could either use, of course, our sensors. You can also consider an up-looking sensor, which is a probe acoustic Doppler mounted on the bottom and looking from the bottom up to the surface. And this is usually for regular profiles, the common method. The SLD, we have deployments running with 1 meter wide channels and 80 centimeter depth of the water. We just take one measurement cell. This works also, but it's an expensive solution for you finally. So it really, I recommend go in touch with us. So send us a message with your cross section where you want to measure, and with the minimum water depth and the maximum water depth, and we can make an assessment and recommend whether our sensors are suitable or not. If not, we can also recommend go with this or this technology. It depends on the site.
Yeah. So there are no more questions at the moment. Please feel also free to contact us after the webinar or join the next webinar this afternoon at 2 p.m. Central East European time. And I would say we're through with this round or session today. I would like to thank you all for your attention and hope to see you soon in another webinar again. Oh, yeah, there was a thank you.
Thank you also from my side. And yeah, as I told you, site assessment is always site specific. So if you have particular sites, please get in touch with us, send us a message, and or send it to the hydro service team or to my hand, and we can then get in contact and give you recommendations. Thank you.